Okay.
Can you all
Perfect.
see me?
Yeah, perfect. You can start.
Visible. Okay, thank you so much. Good day, everyone. My name is Dr. Paul Adedeji from the University of Johannesburg, and I will be presenting the article titled Cluster-Based Wind Turbine Maintenance Prioritization for a Utility Scale Wind Farm. And that is a list of the co-authors with which we worked together on this project, and their affiliations as well as their university logos. Yeah, this is the outline of my presentation and introduction. It is anticipated that renewables will occupy 2/3 of the global energy mix by 2050 if the renewable energy uptake increases by 1.2% annually. And that is what we have observed over the years, that renewable energy is fast taking up the stage in the global energy mix. And we could see the advent of more wind farms being added to the global energy mix. And we can discover, and we've also observed that before in ancient times, we just have one wind turbine, two wind turbines, but now we have large scale wind turbines, of which we have large scale wind farms rather, and we have quite a lot of wind turbines on the farm. And this is not bound to reduce at any moment, but increase at a very high rate. For example, we could see that of the wind farms in Kenya, which is one of the largest in Africa, if not the largest. We could see those in South Africa. We have a lot here in South Africa, and this space is fast increasing. Now, wind resources are associated with strong temporal variability, and that is very, very significant. That is one of the setbacks of wind energy for power generation. And we could see that this strong temporal variability affects the feed into the grid, and it affects the resource availability for each wind turbine. And fortunately, or let me say consequently, the utilization rate of each of the component part of all the wind turbine generators on the wind farm depends on their exposure to the wind resource. And we could see this in one of our studies, in one of our visits. We have partnership with one of the wind farms with which we use their wind farm as a location, as a case study rather. We could see that on the same wind farm, every wind turbine, or each wind turbine, receives wind energy at different proportions. Hence, the utilization rate of the component part of each of those wind turbines differ. And the maintenance activity for each of those wind turbines could also differ consequentially. So wind turbine maintenance has often been challenging because wind turbines are hard to access structures. We have some wind turbines that are 100 meters long from the ground level. There are some that are situated at 80 meters and quite a lot. So many new wind turbines now have cranes that wind turbine operators or maintenance personnel could use to get to the nacelle. And this is very much challenging. Hence, intelligent condition monitoring techniques have been resorted to in recent years. And fourth industrial revolution, which has significantly leveraged the prowess of artificial intelligence in many sectors, is fast increasing. And of course, renewable energy sector is not left behind among the sectors where fourth industrial revolution has been significantly applied. And in fact, the increased driving digitization of renewable energy resources have increased, or let me say, have improved the maintenance and operation procedures and schedules of wind farms through the use of intelligent models which leverage the data collected from supervisory control and data acquisition systems, that's the SCADA, of modern wind farms. And cluster analysis is one of the useful tools that could be deployed on wind farm for maintenance activities. And that is one of those that's the crux of this presentation or this research. For cluster analysis, it uses attributes of objects that are close to one another, or to one another, to cluster them together such that each cluster receives, or each cluster have similar or nearly similar attributes, or with differences between the attributes of one component of a cluster and the same component of the same cluster, not significantly different. And among these cluster analysis or cluster techniques is the Kmeans clustering. And this is an unsupervised learning clustering technique which have been used in wide applications due to its efficiency and effectiveness. What is the motivation for this research? We discovered that wind turbines, the growing demand for electricity in Africa, or let me say globally, has been on the increase, and wind farms are prolifically increasing. Hence, there is need for more strategic planning. And just as I earlier said, for a particular wind farm, on the same wind farm, each wind turbine receives wind energy at different proportions due to the spatio-temporal variability of wind resource. However, if these wind turbines receive wind energy at different proportions, imagine if we now have a very large, a big wind farm with quite a lot of wind turbines, which has, can I call it, of which each of these wind turbines crave for maintenance, or maintenance activities are to be performed on each of these wind turbines. Yes, we have quite a lot of things that are to be considered. However, if like, for example, now if we have 10 wind turbines that needs the same maintenance or nearly the same maintenance all at once, how do we now prioritize? Which one should we go for first? Which one should we go for second? That is the essence. That is actually the motivation for this research, and through the use of clustering techniques. So we aimed at, or this study aimed at clustering the case study wind farm that we used, cluster the number of all the turbines in the wind farm into different clusters based on the wind resource they received, and hence prioritize maintenance activities according to this. Of course, there are quite a lot of factors that should also be considered before embarking on such wind turbine maintenance activity. And that is the motivation for this research. So the methodology, we used Nojoli Wind Farm. Nojoli Wind Farm is one of the wind farms owned by Enel Green Power, an Italian independent power producer in South Africa. And the wind farm is located at the Eastern Power Corridor of the Renewable Energy Development Zones in South Africa. And also the wind farm comprises 44 wind turbine generators, each of which has 2 megawatt installed capacity, which gives the wind farm an aggregate of 88 megawatts installed capacity. So for this study, the wind speed of all the wind turbine generators were collected, which were at 10 minutes data resolution. So the null hypothesis we set before embarking on this study is that there is no variation in the wind speed received by each of the wind turbines on the wind farm. That is, the null hypothesis holds the fact that every wind turbine receives the same wind resource or wind energy, wind speed, of which we tested this using the two-way ANOVA. So we used K-means clustering technique, and of course K-means clustering technique is a parametric method which requires you or the user to spell out the number of clusters to be subjected, or the number of clusters to be expected in the data set. And this is actually one of the challenges of K-means clustering. So we use Carlin-Harrisburg index to obtain the K value for the K-means clustering technique as stated in the equation 1 projected on the slide above. So we use the Euclidean distance metric for obtaining rather the centroid of the mean wind speed for clustering, and this is also stated as in the equation 2 as projected, and the new centroid is calculated using the J function in equation 3. The wind turbine generators receive high wind speed are expected, of course, they're expected to be more productive, and this, of course, most certainly they are susceptible to early maintenance due to continuous movement of road. They need more energy, they are economically viable. However, the back end, the consequence is the maintenance activity on such wind turbine. Okay, so the resultant discussion. So we characterize the wind resource for the wind farm, and from figure 1 we could see the annual energy production of the wind farm, and this was, of course, all the wind turbines on the wind farm are Vestas product, and we investigated the variability of the wind speed across each season of the year on the wind farm, and that is plotted in figure 2. For the summer season, we could see the graph in blue, and for the winter season, we could see the graph in gray, and also the autumn and the spring. We could see periodicity in the wind speeds on each of for each of the seasons, and we could see that for the summer season the wind speed tends to increase, and we could see the time at each of the different time intervals for each of the seasons, and that projects to us that there is variability across the seasons. Also, definitely the wind farm is more viable at some seasons compared to the other. And also we looked at the availability of the wind. Of course, yes, the availability of the wind resource significantly varies from daytime to nighttime, and that is what we could see in that figure 2. The summer period is associated with increased wind speed, and that's we actually did a form of ground verification of this in our site visit to the wind farm at the summer period to verify the result of this variation. And table 1 gives the analysis of variance plot, and we could discover that yes, the null hypothesis says there is no variation between the wind speed obtained at each of the seasons and at each hour and for each of the wind turbines. However, we could discover that the null hypothesis is rejected. Hence, there's a variation between wind speed received from each wind turbine and each of the hours. So we look at the wind farm performance evaluation also, and that is presented in figure 3, and we discover that the wind turbine generation 31 receives low wind speed. Of course, that incurs more cost on reactive power to power the control systems on the wind turbine. And the wind clustering result is presented in figure 4, and we could see that the optimal cluster we obtained was cluster 7. So we embarked on clustering the old wind turbine generators into 7 clusters, and we discovered that cluster 7 receives low wind speeds. Hence, those wind turbines on cluster 7, they are not as productive as those in cluster 6. Definitely, for any wind, if wind farm maintenance, if choices are to be made between the wind turbine generators in cluster 7 and cluster 6, it is wise, based on these clustering techniques that we applied, it is wise to first maintain wind turbine that falls into cluster 6 due to their productivity. Of course, there are quite a lot of other factors that should be considered because this is just part of an ongoing research. So we did not consider the financial impact and all that. That is in the subsequent research that we are presently considering. And let's look at the cluster implications. Wind turbines that belong to cluster 2, 4, and 7 tends to receive low wind speeds and of course reactive power, just as I explained. And if many wind turbines belong to this group, most certainly the power purchase agreement will be affected, because in South Africa, of course, every wind farm owner has a power purchase agreement if they are going to be feeding to the grid. So they have a clear-cut power generation that should be fed into the grid, and of course maintenance activities is also running in parallel. Wind turbine generators that fall to cluster 3, cluster 5, and cluster 6 should be highly prioritized because of their high investment yield, because they receive more wind speeds. Of course, there are other factors in terms of financial factors, availability of personnel, maintenance personnel, and all that should also be considered. But based on the cluster analysis technique, we discovered that cluster 3, cluster 5, and cluster 6 should get high priority. And in conclusion, there is presence of spatio-temporal variability on the wind farm, as we earlier spelled out and as we earlier observed, and wind turbine generators that have wind speeds below 7 meters per second. So of course, there are cut-in speed and cut-out speed for wind turbines. However, there are some of those wind turbine generators that are in a cluster that are not as viable as the rest. So cluster, in conclusion, cost implication for each wind turbine will be considered in future, and that's one of our upcoming research activity. And maximization of profit and cost minimization will also be considered as a form of multi-objective optimization problem. So we acknowledge University of Johannesburg for the support of this research, and also Enel Green Power, the South African company, for producing the data from the SCADA. And these are the references used in this study. And thank you for listening, everyone.